Okay, so there was an issue with live streaming, so we would be recording this session and later on it would be uploaded and the YouTube link would be updated accordingly. So I am the TA for MLF and I will be taking this today's session, which is Solve with Us week 9. Hmm, let me present my screen first. Okay, I hope the screen is visible. So there are a set of questions that we would be solving today. The rules are on the screen. I will be sharing the questions. You would be seeing the questions on the screen. I will be giving you 3 to 5 minutes for each question. It won't take much time to solve them. And you guys can share the answers in the chat. Once I have the answers in the chat, I will begin with the solution and the steps will be discussed. So I hope this particular part is clear.
Yes.
All right. So I guess we can start now. Let me start with the first question. So this is what we have. It's 2:05. I will be discussing this question at 2:10. So let's do that. All right. So I guess I have received more than 50% students answer. So let's discuss this problem. So the question states that, the question is, what will be the constraint equation for the case when you have maximum 3 hours time to solve the whole question paper? So basically, okay, max time is 3 hours, and it takes 10 minutes to solve machine learning foundations problem. So for MLF, uh, which we are denoting with X, it takes how much time? It takes 10 minutes. For the next question, which is maths, we're denoting it with Y. It takes 12 minutes. And English, which we're denoting with Z, it takes 5 minutes. So the first thing that we have to do is convert everything in the same unit. So because this is 3 hours, we will do it 3 into 60, which is equal to 180 minutes. So now the equation would be, it takes 10 minutes to solve one question. So if there are x questions for MLF, then it would be 10x plus 12y plus 5z. This would be less than equal to 180 because the maximum time is given to us, so we can solve the question paper in less time as well. So the constraint would be less than equal to, and hence C is the correct option. So I hope everyone understood the problem. Okay.
Yes, sir. Understood.
All right. Let's move on to the next question. So the next question says that four points are given to you in R2 and they form a convex hull. Which of the following points are the parts of this convex hull? So some points are given in the options. You have to tell which points would lie in the convex hull formed by these 4 points. All right. So I am getting option D as an answer. Is there someone who doesn't know what convex hull means? Please raise your hand or let me know. Okay. So let me first explain what convex hull means. Hmm. Okay, I'll simply open the notes that I took in the TA session. So to understand what convex hull is, we first need to understand what convex combination is. So let's say we have a set of some n points, x1 to xn, and each xi belongs to your RD. And let z be equal to lambda, basically a linear combination of these points. So lambda 1 x1 plus up to lambda n xn. So we will say that this particular Z is a convex combination of points in S if these two conditions are satisfied. Basically, your lambda i's, they need to be more than equal to 0, and the sum of all lambda i's, it needs to be equal to 1. So if these two conditions hold true, then we will say that this Z, which is the linear combination of points in S, this linear combination would be a convex combination. This is basically what we mean by convex combination. So now we use this particular concept to sort of define convex hull. So convex hull of a set S is the set of all Zi's. That's the basic intuition. I mean, simply put, this is what we have. Mathematically, this is the definition that we have. So basically, convex hull of S is simply all a set of all Z's such that Z is equal to summation of lambda I xi. And then there are two conditions. Each lambda I needs to be more than equal to 0, and sum of lambda I needs to be equal to 1. So then let's say we have
So convex hull and hull, what is the difference?
a convex hull and what?
Sorry, convex function and convex hull.
Convex function and convex hull. So they are quite different. I mean, convex hull, I mean, the definitions are different. Function, we are not talking about functions when we are talking about convex hull.
Yeah,
In
it is the linear combination only when we are talking
hmm,
about the function, and if the convex hull is there, then lambda is condition.
are you referring to convex set? I don't understand your question clearly. What two
I
con?
am saying the two definition which you have explained right now.
Okay, so one is convex combination, and okay, so I'll explain it again. So let's say you have a set X of some n points. You have x1, x2, x3 up to xn. Now, using these points, these n points, you form one linear combination. Linear combination is just you multiply each point with a scalar number and then you add them up. So that's what we are saying. Initially, we are just saying that Z is a linear combination. This linear combination will be a convex combination if these two conditions hold true. Now, what are these two conditions? So, okay, first thing, what did we do? We have Z, this is equal to lambda 1 x1 plus up to lambda n xn. Now, we say that this Z belonging to Rd is a convex combination of points in S. What is this S? This S was the original set of points that we had. If these two conditions hold true. So all these lambda i's, they needs to be more than equal to 0, and the sum of lambda I, it needs to be equal to 1. So basically, let's say okay, let me take one example. So let's say you have some points. Okay, I'll take this example when I'm taking convex hull. There I will tell you what I really mean by this zi. So
So,
convex hull. Mhm.
can we say that the set of all that convex functions is convex hull?
Um, I don't
Convex
think so.
combination, I think, or the definition above.
Definition above. Can you repeat the statement that you're saying?
All z, set of all z basically means convex hull. This is what I'm trying to say.
All Zs, the set of
Huh.
all Zs.
Z is basically a linear
Huh.
combination,
Uh,
right?
Z is a convex combination, not just a linear combination.
Convex
Hmm.
combination, and the set of all zi's is convex hull.
Right.
Okay, okay. Thank you.
So that's what we are doing. And then I've taken this one example. Let's say we have 4 points, and these 4 points are these x1, x2, and x3 and x4. Now they will form this one quadrilateral. So this shaded region inside, along with the boundary points, that's going to be our convex hull for these 4 points. And we can take any point inside this shaded region, and some sort of linear combination would exist. So some sort of convex combination would exist. So, for example, let's say we have 1 point and the convex combination is such that we have 0.1 x1 plus 0.5 x2 plus 0.4 x3 plus 0 x4. So, something can exist. So, for every point within this shaded region, we would have one uh, convex combination that would satisfy the condition. So now we have to use this particular concept here. Yes, Varun.
So you said it has to be inside uh, that space. So if something is onto the line, like connecting x1 and x2, it
Yes,
is
that is
part
also
of the null?
included. So
It is
even,
included.
yeah, I mentioned it. Even the boundary points are included.
Okay, got it, got it.
Yeah. So now for this particular question, if okay, uh, so let's say so the points given to us are 0, 0, which would be over here. We have 0, comma 2. Let's say it is somewhere over here. 0. This would be 2. The next point is 2, comma 2, which would be somewhere over here. This is your 2, comma 2, and then we have 2, comma 0. So if we join these points, so this shaded region and including the boundary points, we would have our this is our convex hull. So what are the options given to us? We have -1, comma minus half, which would be somewhere here, which is outside the convex hull. 1, comma -1, again outside our convex hull. -3 and then 1, somewhere here, again outside the convex hull. And then we have 1, comma 1, which would be somewhere here. So this is inside our convex hull. So option D is correct. All right. I hope this particular concept is clear. Okay. Yes, Prashant.
Sir, if the set S contains non-negative vectors, so like in this question, the all the vectors are non-negative, sir.
Mm-hmm.
So the vector containing a negative component will not be part of the convex hull. Will it be?
The points, the set S that I was talking about, the set of points. So it can contain negative vectors as well, but the lambda i's that we are talking about, it needs to be equal to, I mean, it needs to be more than equal to 0, and the sum of all lambdas needs to be 1. So we are not putting restrictions on the points that we have.
No, sir. If it contains only positive points, then negative points will not be in the.
Right. So in that sense, yeah. So if all the points are positive, all the points used to form the convex hull, then yes, negative points, negative vectors would not be part of it.
So we get option D as answer.
Yeah, we can use that as well. Or you can just simply draw it. Both the approaches are correct.
Thank you, sir.
All right. Okay, so the third question that we have is given S is a convex set and the points x1, x2, x3, x4 belonging to S, which of the following points must be the part of the convex hull formed by these points? Okay, so I got a mixed set of response for this particular question. So, okay, given S is a convex set and the points, 4 points are given to us, they belong to the set S. Which of the points, following points must be a part of convex hull? So, according to the definition that I just explained, convex hull is a set of all ZIs, right? Now, what is ZI? ZI is a convex combination. And for convex combination, there were two conditions. The first condition was that each lambda I, it needs to be more than equal to 0. And the second condition was the sum of lambda I, it needs to be equal to 1. So these were the two conditions. So now we have to check these conditions. So in the first question, if we see the sum is not equal to 1, so here sum is not equal to 1, so this would not be true. In the second option, so I got second option as well. So we have these negative lambda i's. So these negative lambda i's cannot be a part because the condition says that each lambda I needs to be more than equal to 0. So this will also be wrong. Now in the third option as well, if we see, we will have 0.1, we will have 0.01, we will have 0.001 plus 0.001. Again, the sum is not equal to 1, so this option is also wrong. But in the option D, if we see the sum, which is 0.25 plus 0.12 plus 0.38, 0.25. This is indeed equal to 1, and each lambda I is also more than equal to 0. So option D is correct and B is wrong. Someone said A as well. It is also wrong. So I hope this question is also clear. Is there any confusion? Saima, I mean, even though in option B we get the sum equal to 1, but the condition of lambda I being more than equal to 0, it does not hold true. So hence option B is
Oh, okay, sir.
yeah. All right. So I guess we can move on to the next question. Okay, so there is one correction in this particular question. This would be 200.
Sir, is it a cube-like box or a cuboidal box?
It would be a cuboidal box. You can consider the height to be equal to h. Okay, so I am getting option B in the chat. So let's discuss this question. So the question says that a storage shed is to be built in the shape of a box with a square base, and they've specified that the square base would be x cross x. It has to be, it is to have a volume of 200 cubic meters. Okay, now fine. The next thing is the concrete for the base costs 50 rupees 50 per square meter. The material for the roof costs 70 per square meter, and the material for the sides cost 60 per square meter. What will be the constraint equation? So in this particular question, you can skip this particular part because the constraint, I mean, the part that I have highlighted with this blue marker, it would be used for some other task, but the constraint equation we can get it just from the first part, which is the volume. So let's say that the height is h and they have given, okay, let's do. So length and breadth are given to us as your x. So what is the formula for volume of a cuboid? It is length into breadth into height. Length, breadth, height. So length and breadth are same. So it would be h x square. And this would be equal to the volume which they've given us to be equal to 200. So this would be the answer. This is your h. So hence option B is correct. So the next thing that they have given us is, I'll write it down because it would be required in the next question. So the concrete for the base costs 50 per square meter. So, okay, let me write it here. For the roof, it would be rupees 70 per meter square. So this is what they have given. Now the next question is, in the previous problem, what will be the objective function? Okay, I cannot zoom it down, but fine. I'll write it over here again. So this is what we have. Now we have to form the objective function. So let's do this now. I'll wait for 2-3 minutes. All right. So I got option C in the chat. Again, I mean, not very difficult to solve. Let's say that the area of the base would be base and the roof would be the same. It would be x square. So we will have 50 x square plus your rupees 70, right? So it would be 70 x square plus, now you have four sides, and for each side it would cost you what? 60 into hx. So this would be the objective function, and when you solve it you will get this as 120 x square plus this would be your 240 hx, and this is indeed the correct option. So option C is correct. I hope this is clear to everyone. Both the parts, fourth question and the fifth question.
Yes, sir.
All right. Okay. So the next question is, which of the following is a convex function in R2? All right, let's take this question now. So, are you guys aware of the method to solve these type of questions? All right. So, fine. So, what we usually do is, if we are talking about, let's say, a single variable function, then we use the double derivative test. So, we apply the same method when we're talking about multivariate. The only difference comes when we're talking about double derivative test in a multivariate setting. We talk about the Hessian matrix. Hessian matrix is nothing but a matrix of double derivatives. So, first, let me tell you what this Hessian matrix is. So, your H for, let's say, two variables, it would be your del square. So this is what Hessian matrix is. You basically have the double derivative with respect to x. You differentiate the function twice with respect to x. Then on the top right corner, you have the differentiate the functions twice with respect to x and then y. Lower left corner, you differentiate the function twice with respect to y and then with respect to x.
No, sir.
And
First with X and then Y, na?
xy or where? Come again.
Uh, at A12, that dou 2f upon dou x dou y, we differentiate first with Y and then X, na?
Both are correct because I've seen both being used. So you can have xx, then xy, yx, and then yy. You can do it the other way around as well. You will get, the answer or the approach that we're going to use, it's going to work for both.
Okay.
All right. And on the lower right corner, we have you differentiate the function twice with respect to y. So if we do that for the first question, you are gonna get, okay, let's talk about this. So when you differentiate this function twice with respect to x, you're gonna get 4, first time you're gonna get 4x and then you will get 4. X and y, because x and y are not together, so you will get 0. Here as well you will get 0, and then with respect to y you will differentiate it twice, so you will get, first time for the first differentiation you will get 10y and then it would be 10. So this is what we have. So let me state the rule which we have. So let me okay, so okay, so these are the two conditions that we have to satisfy. The first condition is that your when you differentiate the function twice with respect to x, it needs to be strictly more than equal, strictly more than 0. And for the second condition is the determinant of your Hessian matrix, it needs to be more than equal to 0. So these are the two conditions. Basically, this element needs to be more than 0 and the determinant of this matrix needs to be more than equal to 0. So if we check it for the first case, 4 is more than 0, so the first condition is satisfied. And the second condition, if we find the determinant, it would be your 40, which is again more than equal to 0. So we can say that this is your convex function. I hope this is clear for the first option. Now
So what if we will be having a three different variable x, y, and z? So in that case, we will get the 3 cross 3 matrix.
Right. In that case, you will get 3 cross 3 matrix,
Yeah.
and there also okay. So there is another method as well. I'm not very sure of the rule for 3 cross 3, but in that particular case, we have two more methods in which you can check for a convex function, and I'll name them. I'll try to describe them after I'm done with this question.
Okay, sir.
Okay.
Sir, but in the exam, this method will be helpful, sir. Other methods, we have to take some data points.
Right. Even from exam point of view, you can expect just a two variable function. So they would rarely give you a three variable function. So not to worry about that. Okay, so the next is minus 3x square minus y square. So in this, what would be the Hessian matrix? So it would be, someone tell me.
-3, 0, 0, -1.
No, you have
minus
to
6
differentiate. Yeah.
minus 6
Minus
0
6, yeah.
0
minus
minus
6, 0, 0,
And then
Minus
minus 2
minus 2.
minus 2. So here the first condition is false because your first element is less than 0. So this is not convex. Even if I sort of try to give you a graphical picture of it, I tried plotting it. Let me. So this function looks something like this. And this is not a convex function, it's more like a concave function. So someone said option B would be correct. That's why I took the graphical tool to plot it. I hope it is clear now.
Yes, sir.
Okay. And in the third question, let me write it here only. So it would be your
4-0.
right
4 0 0 minus 2
4 0 and then
4, 0, 0, minus 2.
now your first element is more than 0, which satisfies the first condition. But if we look at the determinant is equal to -8. And because of this, we will say that, okay, this is not convex. So determinant in this case is less than 0, which is not what we wanted. So that's why your option A is correct, B is incorrect. Okay, so let's have a look at this next question. The minimum value. Okay, before that, I was going to tell you the other methods to check whether a function is convex or not, right? So there are, I mean, so the first method was which I told you, that the top left element, it needs to be more than 0, and the determinant of your Hessian matrix, it needs to be more than equal to 0. This top left of your Hessian matrix. So this was the first test that you can perform. The second test is all.
Sir, why does only the top left have to be more than 0?
Okay, I am not very sure of that. This is just one method that I know. So I'll have
Bottom
to.
right can be greater than 0. That is F Y Y.
Prashant, can you say it once again?
So top left is the fxx. With respect to x, you have to double differentiate.
Mm-hmm.
Bottom right means it will be with respect to y, we have to double differentiate.
Right. So how does this help prove y on the top left.
But we check only for fxx to be greater than 0, not for fyy.
No, I mean, okay.
I'm not asking the reason.
Are you trying to answer the question which was asked, or are you asking the same question?
I'm asking the same question.
Right. So, okay. So I'm not very sure. So I will have to, I mean, it would be best if you ask this question to the instructors, or you can post it on Discourse. I'll take a look at it and then I'll get back to you there.
Okay, sir.
The second test is that all eigenvalues they need to be more than 0. So these are two tests that you can use to check whether a function is convex or not. So there is one more test, but again, I'm not very sure of that particular test. So I'm not gonna mention it right now. But if basically it's something like all pivot elements needs to be more than 0. So that can also be used. But again, I'm not very sure, confident about that particular test. So I'll refrain from mentioning it as well. Maybe someone can post it on Discourse and I'll explain it there. But these are two tests that can be used to check whether a function is convex or not. All right.
And so, what if we will be having a single variable, then we should have checked the second derivative test. It should be greater than 0.
Yes. Second derivative test. In the second derivative test, if it is more than 0, then I guess you get the minima point. So it would be your convex function. And if the second derivative test is less than 0, you get it maximum point, which would be a concave function.
Okay, sir.
So this both the methods involve calculation of Hessian matrix.
Yes. So even here, all eigenvalues of your Hessian matrix. So if you check it, okay, in this particular, let's say that we have this particular example. So if you calculate the eigenvalues, you are gonna get -6 and -2. It need not be true for all Hessian matrices, but for this particular example, it is true. You can try to calculate it. Yeah. Even for other, like this particular case and this particular case, you will get eigenvalues equal to the diagonal elements 4 and 10 here, 4 and -2 over here. So try to use this eigenvalue method as well on the same set of questions and you will realize this thing.
So if all the eigenvalues are positive, then the function will be positive definite. It
Right.
will not be semi-definite, sir.
So right, and then we say that it is, I mean, somewhere this positive definite concept is used to tell whether a function is convex or not.
So sir, convex function can also be positive semi-definite.
Right. Okay.
Positive definite.
Hmm.
No?
Let me confirm this thing. Give me a moment. I mean, what you're mentioning is true, but let me check if the eigenvalues would be more than equal to.
So I guess the eigenvalues will be equal to 0.
Right. Okay. So even if it is equal to 0, then also you can use this thing. So can we move on to the next question?
Yes, sir.
Okay. Okay, I guess we can take it now. So the answer that I got was 1 by 3 or 0.33. Okay, let's have a look. So, I mean, what is the equation for method of Lagrange multiplier? Can someone tell me? Let's say we have two functions. We have f and g. Okay, let me mention it. So if we have a constrained optimization, something like minimize x over f of x, such that your g of x equals 0. If this is what we have, then we have this one equation where your so this is what we have, where this lambda is a constant and it can be positive or negative. So this is what we have, and this is this lambda is what we call as the Lagrange multiplier. So if fine, now what is the equation that we have? So we want to minimize. Give me one moment. Let me. Fine. So we have to minimize this function f of x, y, z. Let me add a new page itself. That would be better. What is the function that we have? We had x square plus y square plus z square, such that your x plus y plus z is equal to 1. Now you can rewrite this as x plus y plus z minus 1 equals to 0. Correct? So this thing you can call it as g of x, y, and z. So this is what we are doing. Now we have the Now we have the function f of x, and we have f of x, y, z, and we have the function g of x, y, z. So what is the equation that we can form out of it? The equation would be this would be equal to your x, y, z. So you have x squared, so it would be 2x. Here it would be 2y, and here it would be 2z, 2z. Similarly, the gradient of your g function, which is yeah, so I've mentioned that this is your g function. So the gradient would be your 1, 1, and 1. Okay, so this is what we have. Now we can simply equate it using the Lagrange equation. So which would mean So I am simply using this particular equation and I'm arriving at this particular solution, this particular equation or expression. So from here, I can say that, okay, now I have 2x equals lambda, 2y equals lambda, and 2z equals lambda. And again, I can simplify it a little more. X is equal to lambda by 2. Your y would be equal to lambda by 2. And your z would be equal to lambda by 2 as well. So this is what we get. Basically, your x, y, and z, all three are equal to each other. Now we know that the function g of x, y, z, this is equal to 0. And we also know x plus y plus z minus 1, this is equal to 0. Now you can use these values in this particular equation. So we'll have lambda by 2 plus lambda by 2 plus lambda by 2 equal to 1. I'm taking this 1 to the right hand side, which would mean 3 lambda by 2 is equal to 1, and your lambda is equal to your 2 by 3. Okay, so simply this is what you get. Fine. So okay, now what was our end goal? We wanted to find the optimal x, y, and z. So x, y, and z, okay, x is equal to y is equal to z, and this was equal to your lambda by 2. So which would mean we can simply use this particular lambda value, and you will get 2 by 3 by 2, so it would be 1 by 3. Correct. So the optimal value, now I'll write it as x star, y star, and z star 1 by 3, 1 by 3, 1 by 3. Okay, so this point is your minima. Okay, can anyone tell me how to get the minimum value out of this point?
Yeah, put these value in the objective function.
Okay, correct. So that's what we're gonna do now. Well, I mean, it was not mentioned, but let's just do it. So f of 1 by 3, 1 by 3, and 1 by 3. If you remember, the function was x square plus y square plus z square. So it would be 1 by 3 square plus which is 3 into 1 by 9 is equal to 1 by 3. And this is your this would be the minimum value. So I hope okay, is there any confusion with this particular question? Anyone who did not understand?
Understood? Yeah.
All right.
So apart from this, what if we will be having an inequality constraint? Then in that case, what are the steps?
So if you have an inequality constraint, so what could be the inequality constraint? It could be where something like your g of x
In
is
that,
less than 0. Let's say you
yeah,
can make
so
it less than 0.
in that case, lambda will be also the inequality value.
Okay, give me one moment. So you're saying if we have an inequality constraint, so what would be the equation or the constraint equation set of equation that we would have? We would have minimize f of x such that your g of x is less than 0. Something like this, you're saying, right?
Yes, sir.
So in that case, your okay, equation with the Lagrange multiplier would be
Fx equal to minus lambda g.
minus lambda del of g of x star. So this is what we would have. Even if I mean now in this case, your lambda, this would be a positive scalar. So and if you want to drop this negative sign, you can do that as well. And okay, I'll write it, or your this would be equal to your lambda del of g of x star. But now in this case, your this would be a negative scalar. So you can, I generally prefer using the second approach. I take, I mean, I completely remove the negative sign from outside. So this is what I personally do. But if you think that this is something you would remember and easier for you can do this as well. And in the case of equality, where we had the constraint equal to something, we can take the negative sign here, and you will still get the same answer. Your lambda value would change to a negative value. So in this case, we got lambda equals to 2 by 3. Your answer would change to negative 2 by 3. And then again, you will get the same answer only. I mean, your values would change at some other places as well. Eventually, the answer that you're gonna get would be the same.
Okay, sir.
Yeah.
And so apart from this, I am having a general question that during our 12th standard, so there is a chapter named LPP, linear programming. So
Mm-hmm.
it seems to be quite similar, that optimization problem. So how it is different from these, why we are moving in a different scenarios. So
So optimization is a field, and I mean LPP. Okay, LPP. If I tell you, there is this other field by the name operations research. There is this big study of LPP, and then there are multiple methods to deal with LPP. This is, will we say that is this an LPP? LPP is a linear. Okay, so LPP is a linear programming problem, right? Here we are not really dealing with a linear problem. We have x square, y square, z square. So apart from LPP, there is also another thing known as non-linear programming problems. So I guess this would fall under that particular category. And then there are multiple methods to deal with LPP. During our 12th class, we used to deal with this thing, graphical method, right?
yes, sir.
So if you get in detail of this OR, operations research, there are other methods as well, simplex method, big M method,
Yes, sir.
and so all these methods are there to deal with LPP. So I guess this particular optimization problem, we want to achieve an optimal value, minimum or maximum, and we are not restricting ourselves to linear equations.
Okay, sir.
Yeah. Okay. So I guess we can move to the next question.
Sir, I didn't get the difference between the less than if there is an inequality. Like you did same for both, I guess.
Okay, I'll tell you. I'll do it side by side. Let me. So this is the difference between the two. You can okay, consider any one of these, either the first one or the second one. You can see that we are restricting the range of this lambda. So if we have the constraint that your g of x needs to be less than 0, then your lambda, if let's for the time being assume that only the first thing is what we have. I'll remove the second one. Okay. So in the first case, we have, okay, I'll also, okay, let's take the same equation again. So the restriction on this Lagrange multiplier is that we will only allow it to take negative scalar values. But on the right hand side, where we have this g of x equal to 0, we can take either positive or negative scalars. So this is the difference between both the equations. I mean, to understand it better, I guess you should watch the lecture. There, Arun sir has explained it using some graphs. So he has taken some graphs to explain this concept, why this needs to be there.
Okay, sir.
So what if g of x is less than or equal to 0?
If it is less than equal to 0, mm, okay, in that case, what can we do? Let me see. I guess we can settle for this left hand side equation itself in that particular case. Again, I will have to confirm this. I'm not very sure of this. Okay, I'll get back to you with this as well. Let me write it down. But most probably you can settle for the left hand side.
Okay, sir.
Right. And can you also remind me of the other doubt that came up? Okay, yeah, it was.
Sir, I posted it on Discourse.
Okay, you did? All right. Cool. Okay, so the next question is, what is the boundary value of phi so that the function is to remain convex? So for what value of y would this function remain convex? Okay, give me 2-3 minutes. I'll go drink water. By the time, please try to solve it. All right, I just got one response for option C. It is quite similar to what we have been doing till now. We again have to, I mean, what was the test that we were doing for convex functions? We were using the Hessian matrix, right? So that is exactly what we have to do. So we'll calculate the Hessian matrix for this particular function. And what would be the Hessian matrix? It would be the first derivative 2 and then we'll get 2. And because no variables are together, you're going to get 0 0. And then again similarly for this as well. So this would be the Hessian matrix for this particular function, which is x minus 3 whole square plus y plus 1 whole square. And because you can see that in this case your condition, both the conditions are always true no matter what the value of y is. The first condition was this needs to be more than 0, and the second condition was that the determinant, it needs to be more than equal to 0. So if we see your first element, it does not depend on y, so it is more than 0. So this is always true. By always, I mean for any value of y. And if you talk about the determinant, your determinant is equal to 4. So again, irrespective of the value of y, your determinant is more than equal to 0. So again, always true. So because of that, your option C is the correct one. For any value of y, function will remain convex. So I mean, okay, let's say we had some other function for which you were to receive the following Hessian matrix 2 0 0, let's say 2y plus 5. So can you take 2 minutes to find for what value of y would this remain a convex function? So I don't have the function, I'm just like randomly forming this Hessian matrix. Let's take 1 or 2 minutes. It would take just 1 minute to find the value of y for which this would be your convex. Right, minus 5 by 2. But you need to give me some range, not just a number. Would it be less than or more than? What would it be? So you're saying that this needs to be more than 5 by 2. Is it? Okay, this is still a little wrong. Yes, more than equal to. Yes, Prashant. So the condition is that your determinant. Okay, fine. So the first thing is your this element needs to be more than equal to more than 0, which is true. You will find the y value using the second condition, which is determinant more than equal to. So that is what you will do. And in this case, it would be your determinant would be 4y plus 10 more than equal to 0, which would give you 4y more than equal to minus 10, y more than equal to minus 10 by 4, which means y more than equal to minus 5 by 2. So this is
Sir,
what
can
we
you
have.
repeat? My connection was lost.
All
Sorry.
right, all right, all right. So I mean, uh, what part do I repeat? The second example that I took, or the question itself?
Question.
Okay. So the question was, what is the boundary value of y such that this particular function is to remain convex? So the method is what we have been using till now. You calculate the Hessian matrix, and the Hessian matrix for this particular function is given over here. So the Hessian matrix would be your 2, 0, 0, 2. If you differentiate it twice with respect to x, you're gonna get your 2. With respect to y, you're gonna get 2. Because x and y are not together, so you're gonna get 0 and 0 on the other diagonal elements. So fine, this is the Hessian matrix. Now the two conditions for it to for the convexity were that your this thing, the upper left element, which is differentiating your function twice with respect to x, it needs to be more than 0. And because this value is 2, so it would be always true. By always, I mean for any value of y. Okay. And the second condition was your determinant needs to be more than equal to 0. Again, we calculated the determinant and it was equal to 4. So irrespective of the value of y, your determinant would be more than equal to 0 always. So that's why option C is the correct one. For any value of y, function will remain convex.
And if it is asked for x, then the value would be greater than 3 or greater than equals to 3.
Right.
Okay. Thank you, sir.
Okay. Then I took this other thing that let's say you are, yes.
Sir, even for x, it should be option C, right?
So even okay, let me.
Sir, I was asking for another question that if it is asked in case of x, then
In case of x, yes.
like if the options are given like x is greater than equals to 1, greater than equals to 2, and so.
I guess it would not be given for x because okay, if even for x, it would remain for any value of x, it would remain a convex function because again, your Hessian matrix is not really dependent on x, so it needs
Sir,
not.
but if the value, it is independent of the value of x.
Yes, the Hessian matrix is independent of your x or y.
Okay.
So it would not depend on your, I mean, it would not depend on the value of x either, at least this particular function. So that's why to explain this concept a little more, I took this other example. Let's say your Hessian matrix was equal to 2, 0, 0, 2y plus 5. So in that case, what would be the value or what would be the value of 5 for which the function remains convex? So then, I mean, your pivot element is 2. So
So how we get this 2y plus 5?
this I'm taking a random Hessian matrix. I don't have the function available for it. I just took, okay, let's say there is some function for which you get this particular Hessian matrix. So this is a separate question, not related to the question that was there.
Okay.
Yeah. So I was just like taking an arbitrary example. Let's say that there is this Hessian matrix where you have this.
So could you please explain this question again? It's
Question 8 or this particular question that
question
I took?
answer, sir. So after these two conditions being satisfied.
Okay. So after these two conditions are satisfied, we said that option C is correct. For any value of y, the function will remain convex. Consider, okay.
Okay.
Consider this to be your question 9. Another question. I took another question where I'm saying, oh, I hope this particular question 8 is clear.
Yes, sir.
Because I mean, both the conditions are true, always true. So we can say that this function is convex and it does not depend on the value of y. For any value of y, you will have this function as convex. To explain the concept, why, I mean, let's say to explain the concept a little more, I took this other question, which I'm calling as question 9 for the time being. So let's say you are given the Hessian matrix which is equal to your 2, 0, 0, 2y plus 5. Then the question is, for what value of y would this function remain a convex function? So then what did we do? Again, we were verifying the two conditions. The first condition was to check whether this element, upper left element, is more than 0. It is more than 0. So the first condition is true. Now the second condition was your determinant needs to be more than equal to 0. So we calculate the determinant, and that's what we have done. So the determinant is calculated as 4y plus 10, and this needs to be equal to more than 0. So this is the condition, right? This left hand side is the determinant, and left hand side needs to be more than equal to 0. Then I just solve this inequality and I arrive at the solution that your y needs to be more than equal to minus 5 by 2.
Understood.
Mahi, is there any question?
Sir, actually, I want to know that d square x by dx dy, sir, how it come to be 0?
Where exactly?
In the equation forming the Hessian matrix.
In this
0.
particular case?
Yes, sir.
So you different, okay,
The 0 part.
0 part.
D square x by dx by dy equals to 0.
Is this what you're talking about?
Yeah.
This would be your f, first of all. So, I mean, first you differentiate it with respect to x. What are you going to get? You will get 2x minus 3. Now you differentiate it with respect to y. Because you don't have any y, so the next step, you will get 0. Okay, I'll explain it again. Let me, where do I write it? So, this is basically, I mean, you take the, do you understand what do we mean by second derivative?
Yes, sir.
So the second derivative means you take the first derivative and then you differentiate it again.
Okay.
So let's take the upper left element. So what would that be equal to? The first derivative would be your 2 times x minus 3. Now you differentiate it again. So now this would be d by d of x, and then it would be equal to 2. I hope the upper left element is clear. Why we get 2?
Yes, sir.
Okay, so fine. This is what we get. Now the next thing that we have is this thing. This means that you first differentiate the function with respect to x, and then you differentiate it with respect to y. So which would mean, what would be the differentiation of the function with respect to x?
2x.
2x minus 3. Or you can say it would be 2x minus 6. Correct? Now this is your df by dx. Now you differentiate this function with respect to y. So what would be that? It would be 0 because there is no y variable. Differentiating with respect to y means you keep x as constant, and derivative of a constant is simply 0. So that's why it would be, for this particular term, it would be 0, minus for 6, it would be again 0. So which means this element would be 0. Okay.
Yes, sir.
Now let's take the other case, which is this thing, lower left element. So it means you first differentiate with respect to y, and then you differentiate it with respect to x. So in this case, what would be your df of dy? Can you tell me?
2y plus 1.
2y plus 1, right? 2 into y plus 1.
Yeah.
Now you take this thing, this first derivative with respect to
And
y.
differentiate with respect to x.
Yeah, and because we don't have, so with respect to x, it means any other variable, you treat them as constant. So because,
Okay.
so with respect to x means you will treat y as constant, and then you will get the derivative as 0. And then in the third case, you will get again equal to 2.
Yeah. Got it.
Yeah.
Thank you, sir.
Okay, no issues. So one more thing I wanted to take. So what does it mean when we are finding a range on y? So we are saying what is the boundary value of y so that so and so function remain convex. So it would, I mean, graphically, if we were to understand this thing, it would mean that you have some sort of function which is convex for one particular range, but after that point, it is not convex. So maybe, I mean, I'm taking it to be in the case of a single variable. Basically, what does it mean that for this particular range, there's a, I mean, in the below question, we're talking about two variables, so I cannot demonstrate it in a 3D setting on paper. But let's say you were talking about one variable and you got some range, x less than equal to this particular point, x star, less than equal to x star. And this point is your x star. So it would mean that your function that you have, it would be a convex function below this thing. So that's what it means. After that, if you take any value of x, if you take this value, then your function would not remain convex anymore. So graphically, you can think of it in this way. So this is what we have, and this is the final, okay, final question that we have. So which of the following Hessian matrix corresponds to the convex function? So again, very easy. We have been doing this all along. Okay, please repeat that graphical part. Okay, let me take this. So, okay. So what I'm trying to explain is that we were trying to find a boundary value for y such that this function remains convex, right? So I'm not taking an example of a two multivariate function, but let's say you have a single a function in a single variable, let's say x, and your function's graph or something like this. Maybe let's say it could be anything, but there is one part where it remains your, okay. This is what we have, right? Let me take the screen pen, make it purple. So if you see, there is this one part where your function, I mean this particular part, if you see, your function is a convex function. But the moment you step to the right part, it is not convex anymore, correct? So this is what I'm trying to explain, that this is what we have. I mean, this thing would go beyond as well. We're not restricting ourselves. So this is like the, I mean, our function is convex over here. let's say this is your x star. So in the question we were doing y less than or y less than equal to or y more than equal to, let's say we got 5/2, right? So in this case, I'm taking a similar example to explain it graphically. Let's say we got your x less than x star or less than equal to. Let's say your x is less than equal to, let's say 5, and this x star is equal to 5. So in that case, what does it mean graphically? It means that your x equals to 5 is the boundary point beyond which your function would not be convex anymore. In this case, to the left hand side, your function is convex. I mean, I've not drawn it properly, but if you see, it is a convex function to the left hand side. But the moment you take a step to the right hand side, maybe let's say here, then your function would be something like this, and it's not convex anymore. So that's what,
Okay, so thank you.
yeah, that's what I was trying to explain. Okay, let's solve this last question for today.
Hello, sir.
Yes, someone was saying something.
So after this question, can I ask a doubt from activity?
Sure, we can take it. Okay. So So this is again the same concept that we have to use. You can already eliminate this and this because your top left element, they are negative. So the first condition does not hold true for these Hessian matrices. So that's why we eliminate them. Now in the B and D, we have to, okay, the first condition is satisfied, but we have to satisfy the second condition. So we find the determinant. So what would be the determinant? It would be 15 minus 1, which would be equal to 14, which is more than equal to 0. And in this case, so yes, B is a Hessian matrix corresponding to a convex function. In the D part, we have the determinant equal to 15 minus 4 equals to 11, which is again more than equal to 0. So again, your D is also a convex function, a Hessian matrix corresponding to a convex function. So I hope it is clear to everyone.
Yes, sir.
Okay. What is the question that you have?
Activity 9.4. You have that.
There is a background noise from your end. Can you type the question in the chat?
Now,
Okay, yeah, it's better.
activity 9.4.
Mhm. Question
And
number.
four and first, I'm confused little bit.
First question.
That is lambda belongs to 0, 1. Now it is
Uh, okay. So this question was taken on discourse, I believe. So initially, I also thought that this question is wrong, but on discourse, Karthik sir or I guess Karthik sir took this question. Let me try to find it first. One moment. Okay. So this was the question, right? The first question from activity 9.4.
yeah, yes, sir.
So the answer is indeed can be any range. Basically, what Karthik sir is trying to explain is that x3 is in fact on the line joining x1 and x2. It does not necessarily mean that the line segment joining x1 and x2. I mean, if you see that you can have 2 points joining x1 and x2, and you can extend it outside as well. So x3 can lie on an outside point, but it would still be there in the convex set. So if your lambda belongs to 0 comma 1, then x3 indeed lies on this particular line segment. But if your lambda does not belong to 0 1, then it lies outside this line segmented, but it is still very much part of this extended line. That's what he is trying to explain. So another way of understanding is your x3 is equal to x2 plus lambda times x1 minus x2. So x1 minus x2 is a vector from x1 and x2. So is this definition sort of clear to you?
So
Mm-hmm.
I have a doubt like whether what is the relation between convex set and convex hull? Like whether every convex set is a convex hull or
Okay, so the relation between the two, basically, no, every convex set. Okay, will we call every convex set to be a convex hull? No, because when we talk about a convex set, we are taking 2 points, x1, x2, and then we're talking about the what do you say, convex combination of these 2 points, and we see if that particular point belongs to the convex set S or not. But in the case of convex hull, what are we doing? It is, I mean, we have some points which belong to some convex set. So let's say we took 4 points during the question as well. We took 4 points, right? So now that convex hull would be a combination of, I mean, it would not necessarily be. I mean, they're not same, but a convex hull is a convex set. So this is, I mean, a property of convex hull. Every convex hull would be a convex set.
Okay, sir. Thank you.
But a convex, okay. But I mean, every convex hull is a convex set, but every convex set being a convex hull, that is not true.
Then intersection of that set will be a convex.
Yes, intersection of two convex set is a convex set.
Okay, sir. Understood.
Okay, if the convex set is 1 comma 3 and we take x1 to be 1 and x2 to be equal to 3. Prashant, what is your question exactly?
No, sir. You said that Karthik sir told that the lambda can be in any range.
So the convex set in the question is given in R2. Your convex set is restricting to 1 comma 3, but in the question it says that the convex set is in R2.
No, for example, if we take convex set to be 1, 3,
Mm-hmm.
then lambda should be between 0 and 1, sir. If we take like x1 to be 1 and x2 to be 3.
Right. If your I mean, if the convex set is what you have defined, then in that case your lambda must be between 0 and 1, 0, 1 both included. But given the question uh, in the activity question, there they have specified the range, the convex set to be in R2. So that's why, I mean, your lambda is not really restricted to just 0 and 1. It can take any value and it would lie in R2. Any point, I mean, the linear
Sir, so
combination.
lambda's value will depend on, or its range will be depend on the function we define.
So it would, I mean, it would be usually what is the case, the S, which is your convex set. That will, I mean, the definition. Okay, let me share my screen again. Hmm. Okay, so I took this session in the TA open session. A recording would also be available to you guys. So you can check that where I have explained it. Basically, if you have a set S, which is a subset of RD, in that case, your lambda would be between 0 and 1. So that's what we have. But if it is equal to RD, in the case of your question, it was equal to your R2, right? In that case, your lambda can take any value and any other point would also be in R2, correct? So that's why in that particular activity question, your range was not restricted to 0 and 1. But if you're taking some other restricted set, even though I have mentioned subset or equal to, but if it is equal to, I mean, if your S is equal to, let's say, some RD, then also this condition would hold true, but your lambda can take any value. This is something if your S is equal to RD. But if your S is a subset of RD, then I mean, this restriction would be there. I mean, this is the definition that we are using. At least 0 and 0 comma 1, this particular range should satisfy. So this is what we have. Okay,
So please
Saima,
post this PDF, the notes PDF that you have on the
uh,
section link.
this one.
Yes, sir.
Okay, I shared it in the TS session as well. I'll do it right now. Give me one moment. This was intro to convexity. Okay, I have pasted it. What I'll do is I'll also try to. because this session is being recorded, so if someone wants, they might use this particular link. Okay, so I'll stop the recording as well now.